Introduction: How asphalt is made. In the story of human progress, asphalt stands out as one of the boldest strokes. More than just a surface, it is the foundation of trade, cities, and global connection. Over 40 million miles of asphalt roads cover the planet, proving that behind the speed and prosperity of the modern world lies a dark, modest invention that quietly holds everything together. Yet this black coating, which looks so simple, goes through a demanding journey. Before reaching the road, crude oil, formed over millions of years underground, is fed into towering distillation units, where the heaviest and thickest fractions are separated. After further refining, this dense black material is transported, heated, and spread across roadbeds, creating the solid ground that carries commerce, travel, and global exchange. So, what hidden secrets lie beneath this unassuming layer that supports an entire civilization? Stay with us until the end of the video to discover the full story of this humble yet vital invention. Asphalt, the backbone of modern infrastructure. The asphalt industry is a pillar of modern infrastructure. Every year, its global market value exceeds $300 billion, with more than 1.6 billion tons of material produced to maintain and expand transportation networks. It generates millions of jobs and drives commerce, but it also comes with heavy environmental costs. The consumption of petroleum, massive emissions, and intense pressure on ecosystems. And yet, asphalt carries a remarkable trait: it can be recycled almost endlessly. Every layer of old pavement can be crushed, reheated, and reused in new roads without losing its strength. This regenerative ability opens the door to a more sustainable industry, one where the miles already traveled are not wasted, but reborn as the foundation for the miles ahead. A cycle without end, preserving economic value while easing the weight of our environmental footprint. Crude oil extraction and distillation. The journey of asphalt begins with crude oil, a resource extracted in two main ways: offshore drilling and onshore wells. Both aim to bring the black liquid from deep underground to the surface, but each demands its own set of technical solutions. Offshore, massive drilling rigs stand firm against wind and waves, operating like floating cities. From the drill floor, a steel bit drives through seawater and plunges into seabed sediments, sometimes reaching depths of 9,000 feet. At such pressure, exceeding 3,000 psi, engineers must carefully control every parameter. Special drilling fluids are constantly pumped down to cool the bit, stabilize the well walls, and carry rock cuttings back up. At the wellhead, multi-layer blowout preventers act as a shield against sudden eruptions, while hundreds of sensors feed real-time data to the control room. Once conditions are stabilized, dark crude oil is allowed to flow upward through pipelines, collected in floating storage tanks, and transferred to tankers bound for shore. Out in the open sea, these rigs stand like steel fortresses, defying storms for decades. Do you know how engineers make them stable enough to withstand such forces? Share your thoughts in the comments. I'll be reading them all. On land, conditions are steadier, but the process mirrors offshore drilling. Towering rigs send steel bits thousands of feet down through layers of rock to reach oil reservoirs. Drilling fluids once again cool the bit, protect the well, and keep the borehole stable. In high-pressure fields, crude oil can surge naturally to the surface, while in lower-pressure sites, the familiar nodding donkeys, mechanical pump jacks, rhythmically lift oil to daylight at the surface. The crude is gathered in giant storage tanks, then shipped by pipeline or tanker trucks to refineries. Whether from remote seas or vast plains, the outcome is the same: streams of dark crude drawn from the depths of the earth, the essential first step in asphalt's long journey. Once crude oil leaves the well and is transported to the refinery, it enters the very first stage of processing: distillation. The dark liquid is pumped through a heating system where it is gradually raised to about 660 to 750 degrees Fahrenheit, equivalent to 350 to 400 degrees Celsius.
At this high temperature, the mixture begins to separate into fractions according to molecular weight and volatility. Inside the towering distillation column, the fractions settle in an orderly way. At the top, lighter components such as gases, gasoline, and kerosene condense into liquids. In the middle layers, diesel appears, while heavier materials flow down to the lower trays. At the very bottom, where heat and pressure are greatest, the heaviest part of crude oil remains as a dense black liquid. After further refining, this dense black material becomes the raw material for asphalt production. The entire operation must be monitored continuously. A network of sensors measures temperature, pressure, and flow at each stage, ensuring that every fraction is drawn off at the correct threshold. The end result is that crude oil, once a chaotic mixture, is neatly divided into distinct parts, where the heavy bottom fraction serves as the key to building the roads of the modern world. Aggregate mining and processing. In the journey of asphalt production, crude oil is not enough. The other essential component is stone aggregate. Open-pit quarries are developed in mountain ranges rich in hard rock, such as granite, basalt, and limestone, materials valued for their compressive strength and resistance to abrasion. The process begins with the removal of thick layers of overburden, sometimes dozens of feet deep. Next, workers drill a grid of deep holes, carefully load them with measured amounts of explosives, and set off a controlled blast. The mountainside trembles, breaking into massive slabs that crash down to the quarry floor. Right after the blast, excavators and heavy-duty trucks move in, hauling thousands of tons of rock onto dedicated haul roads. From there, each load is transported directly to the aggregate plant. At the intake hopper, the stone is fed into a series of crushers that reduce it into various sizes, from coarse gravel down to fine sand. Conveyors and vibrating screens work non-stop, classifying each fraction according to strict technical standards. Once sorted and stored in separate silos, the aggregate becomes the skeleton of asphalt. Large stones provide structure, medium particles fill the gaps, and the fines bind the entire mix together. This precise combination forms the foundation of the strong black pavement that supports modern roads. Hot mix asphalt production process. When crude oil has been distilled to obtain the heavy fraction and aggregate has been crushed and screened, both converge at the asphalt mixing plant, the place that defines the final quality of asphalt. From storage bins, aggregate is discharged onto steel conveyors and carried into a rotary dryer, stretching dozens of meters long. Direct flames heat the material to over 300 degrees Fahrenheit, about 150 degrees Celsius. Inside the rotary dryer, the aggregate tumbles continuously within the rotating drum, while high-powered fans draw out every trace of moisture, ensuring each stone is completely dry before blending. Exiting the dryer, the hot aggregate is lifted into a multi-deck vibrating screen tower.
Powerful vibrations classify the material by size. Large stones form the framework, medium grains fill the gaps, and fine particles bind the entire structure together. Electronic weighing systems immediately measure each fraction, combining them according to a preset mixing formula. At the same time, the heavy oil fraction, drawn from the bottom of the distillation tower, kept fluid by preheating to 300 to 320 degrees Fahrenheit, is pumped steadily through pipelines, ready to merge with the aggregate. All of this flows into the forced mixer, a sealed steel chamber with two massive counter-rotating shafts. Their motion blends the materials thoroughly, coating every grain of aggregate with hot binder and filling every gap. A mixing cycle lasts about 30 to 45 seconds, with temperature carefully maintained so the blend is neither too stiff nor too runny. The entire process is closely monitored by a central computer system, from material ratios to mixing time, ensuring every batch achieves uniform quality. When the mixing cycle ends, the hot asphalt mix is discharged into a heated surge hopper located just beneath the mixer. This is a crucial intermediate step.
The hopper keeps the temperature steady at about 275 to 300 degrees Fahrenheit, roughly 135 to 150 degrees Celsius, and prevents the asphalt from sticking together. From the hopper, the mix is gradually released into the hot storage bin, where mechanical paddles constantly stir the material so it does not segregate or clump. Only then does the specialized dump truck move into position beneath the discharge gate. The entire bed and sidewalls of the truck have been coated with an anti-stick layer, ready to receive the hot load of asphalt. Once the truck is filled, the mix is immediately covered with an insulated tarp to retain heat, preparing it for the short but critical journey to the paving site. As soon as the dump truck leaves the plant, the hot asphalt mix must be kept at the proper temperature throughout the journey. At the construction site, the truck reverses directly into the asphalt paver and unloads the mix into its receiving hopper. From there, conveyors and augers distribute the material to the rear, laying it down as a continuous layer across the prepared roadbed. At the back, the screed, controlled by hydraulics and guided by laser sensors, ensures the mat is laid with the exact thickness, smoothness, and slope required by design. While the asphalt is still hot, a fleet of heavy rollers immediately takes position. First comes the smooth steel drum roller, giving the mat its initial compaction. Next, the rubber tire roller, weighing tens of tons, presses the aggregate tightly together, sealing the voids. Finally, the vibrating steel roller finishes the surface, increasing density while leaving it smooth and even throughout. The entire process is closely monitored by the temperature of the mix, because once it cools below 200 degrees Fahrenheit, about 95 degrees Celsius, the asphalt hardens and loses its ability to bond. When compaction is complete, the pavement still retains high heat. Workers then spray water across the surface, both to cool it down and as a direct test of quality. If the road meets standards, the water quickly spreads evenly, seeps into tiny gaps, and drains smoothly to the sides. On the other hand, if puddles, bubbles, or hairline cracks appear, it signals that the layer has not achieved proper density. Alongside the water test, engineers continue with precision checks. Laser devices measure flatness and slope, while core samples are drilled and taken to the laboratory for analysis. Only when every parameter, from compaction and impermeability to drainage performance, meets the required thresholds, can the pavement be officially approved and handed over, ready to bear the weight of thousands of vehicles each day. At this point, a new asphalt road has taken shape, black, smooth, resilient, and strong enough to withstand relentless traffic. It marks the end of the production process, but also the beginning of millions of new journeys around the world. Recycling asphalt, reclaimed asphalt pavement. In the life cycle of a road, when the surface layer becomes worn, it is not discarded, but reclaimed for recycling. Specialized milling machines cut away several inches of old asphalt, grinding it into small particles on site. This material, known as RAP, reclaimed asphalt pavement, contains both used aggregates and aged binder still clinging to the stone. Tons of RAP are transported back to the plant, unloaded into dedicated storage bins for reuse. At the plant, RAP undergoes a closed-loop process. First, the reclaimed material is fed into a rotary heating drum, where hot air removes moisture and softens the aged binder. Next, it passes through vibrating screens to be sorted by particle size. Part of it is fed directly into the mixer along with fresh aggregates, while the rest can be stored as supplemental material. At the same time, new binder, virgin asphalt, is pumped in and blended with the RAP in carefully measured proportions by electronic scales. This restores the flexibility and strength lost in the old pavement, creating a uniform mix that meets technical standards. Beyond plant recycling, Many regions also adopt in-place recycling. In this method, specialized machines mill the old surface while spraying rejuvenating liquid binder directly onto the road, which is then compacted immediately on site. This approach saves transport costs and reduces road closure times. The result is clear. Instead of becoming waste, nearly every ton of worn pavement is returned to serve new roads. Some modern facilities now achieve 100% recycled content, making asphalt one of the longest-lived construction materials. This not only saves millions of tons of rock and crude oil each year, but also significantly reduces CO2 emissions. Asphalt is not just the foundation of modern transportation, it is proof that infrastructure can also follow a sustainable path into the future. Conclusion: building millions of miles of roads. From offshore wells drilled thousands of feet deep, where immense pressure is controlled, down to every side, from open-pit quarries where thousands of tons of granite and basalt are blasted apart, to the towering distillation columns and non-stop hot mix plants, every stage combines into a complex chain of technology, all to produce the asphalt surface we walk and drive on every single day. On the outside, it looks like nothing more than a black layer, but within it lies engineering, energy, and human ingenuity. Today, thanks to recycling technology, asphalt's life cycle has almost no end. Old pavement is milled, remixed, and reborn as part of new roads. In this way, millions of tons of crude oil and stone aggregate are saved each year, reducing environmental pressure while sustaining the transportation networks that serve billions of journeys. Asphalt has grown from a modest invention into a silent pillar of modern civilization, linking city to city, trade to trade, and people to people. And you, when you see a freshly paved road, what impresses you most? The raw power of extraction, the precision of technology, or the infinite ability of this material to be reborn? Share your thoughts in the comments below. And if you want to uncover more hidden stories behind everyday materials, don't forget to follow. Our next journey will surely bring even more surprises.